I'm Jenna Saylor, and this is my lab report for on circuits. Purpose of the lab. Use the principles of energy conservation and current conservation to predict the behavior of circuits with resistors in series and parallel configurations. Use multimeters to measure values of conventional currents and potential differences in circuits, and to examine the behavior of ohmic restrict resistors and capacitors. Some important concepts to understand are the loop rule, which basically says that all the potential differences sum up to zero. The node rule, which just states that the currents all have to be equal to each other in a series. If it was parallel, it would be I1 is equal to I2 plus I3. Ohm's law, which is potential difference equal to the current times the resistance. Energy and current conservation, just everything in a current all should be equal and sum up. You can't lose any. And then finally, just be familiar with circuit components, batteries, resistors, capacitors, emitters, and voltmeters. A preview of my results. Potential difference is zero. The current is 0.02 amps. And then these are just some of the resistances calculated, which was potential difference over current. Experiment. During the experiment, we had to build circuits and then answer the following questions. So first thing, we needed to predict what we think the circuit was. And up on the top right corner was my calculations. And I actually got it right, so that's fun. And I also spelled definitely wrong, so just ignore that. Um, but so I predicted that the current was 0.02 amps. And then when I ran the simulation, it was also 0.02. If you put the ammeter backwards, it still reads the same thing. The voltmeter said that there was 3 volts in the whole current, which is true and holds true to energy conservation because the energy in the loop must stay in the loop. And then here were the potential difference calculated with the voltmeter. We just put it at every single point to calculate them. And as predicted, they summed up to zero. The experiment continued. This is a graph of our results. It just shows the slope at different times. So we can see it starts at 0, goes up to 3, then it ends up going back down to 0, hence conservation. The ammeter reading does not change with the addition to a voltmeter because it's basically just extending the wire, doesn't have any resistance in the model. And the reading was negative 2.04 across the 100 ohm resistor. And when it was placed in a parallel circuit, so it was the wire and then it split off into 2 branches. One was the resistor and one was the ammeter. It read 0.06, and this was because less of the current is diminished through the resistor since only half of it's going. So the total current is going to be higher. And then down here are just the resistance calculated. I showed in the results, but here they are again. And that was just potential difference over current. And then finally, for the last part of the experiment, we had to set up a circuit with a 9-volt battery, a capacitor, light bulb, and then measure the voltage across. So we did that, and the voltmeter read 9 volts. The time graph agrees, and at the very end of the video, I'll put in a picture of the time graph. What if? So what if you were doing this lab in real life and use an actual ammeter instead? What is different about it, and how would it have affected the circuits? So a real ammeter is going to have some small resistance, and it would just make the results less accurate to what the computer model showed. And then if we were to do this again in real life and use a real battery to charge a real capacitor, how quickly would the model predict in comparison to real life? So the ideal model obviously is instantaneously because it just does it immediately. In real life, capacitors build charge up over time, so the prediction would still happen, just at a much slower rate. Finally, some errors that could have been present in the lab that skewed the results were inaccurate circuit building, less precise numbers, because it only rounded to 2 decimal places, and then, once again, not an exact replica of reality. Thank you.